My name is Alan, and I'm presenting my study on the manufacture of titanium 64 alloy using the CMT wire arc additive manufacturing process. Let me introduce the titanium 64 alloy to you. It is one of the most popular materials used in the aerospace industry and constitutes more than 15% uh, of the modern aircraft such as Airbus A350. However, the aerospace industry faces several drawbacks in the form of very high material utilization factors, wherein the material that is used to manufacture parts of complex geometry, such as engine parts, is much more heavier than the actual part which is eventually developed. So there is this huge amount of material wastage, and that translates into heavy financial losses. Now, this is where additive manufacturing comes into play. Additive manufacturing deposits material onto a workbench, and therefore it does not involve removal of material, and the material utilization factor therefore is consequently very high. This additive manufacturing process can be split into different categories on the basis of the source of energy that's used and the form of material that is used. However, when we look at the different properties of each performance of each system, we realize that the wire and arc additive manufacturing system has several advantages over the others in terms of cost, speed, and ease of training and knowledge. So this is the average a simple wire and arc additive manufacturing system schematic. It involves the use of torch with a wire feeder. So the torch melts the wire that is being fed through the wire feeder, and it is driven by a robot to deposit layers of material on a substrate. This substrate acts as a workbench, and by adding layers of material over one another, we are able to produce the final part. There are several advantages and disadvantages to this process. However, looking at the disadvantages, it is mainly poor geometrical accuracy, buildup of residual stresses and distortions in the part. After clamping of the part from the workpiece, we have distortions that take place which affect the geometrical accuracy. And this is all aided by a very non-linear and highly coupled input-output parameters of the welding process, which makes it very difficult to control. There are different ways in which the arc can be created using different welding processes. The most popular is the gas metal arc welding process, which involves the electrode being the wire being fed in the electrode being fed into the torch for melting and use as the material to be deposited. This makes sure that the cost of equipment is much more lower, since no additional mechanisms for a separate wire feeding mechanism is required. It also has higher deposition rates and is cheaper on the whole run. However, it has several disadvantages in the form of poorer surface quality, which is improved upon by the recent advances in the technology by the use of a cold metal transfer technology, which involves a lower heat affected zone, lower temperatures generated at the torch, so therefore the surface quality is greater and very less spatter takes place. Now, there are two major areas of research that is taking place in the world in this area. One is at the University of Wollongong, and the other is at Cranfield University. While Cranfield University has focused more on the material properties and improving the microstructure and relieving residual stresses of the deposited parts, the University of Wollongong has focused more on the tool path planning and the avoidance of creation of voids when the material is deposited in the final, and the final part is having good geometrical accuracy. So this is the system that was developed at the University of Wollongong for taking a CAD part at the start and going on to produce the final end material with no human interaction in between. So in this, the CAD model is first sliced using an adaptive slicing mechanism, and then it is this data is used to plan the tool path for deposition of the material, This is aided by a very comprehensive comprehensive process model, which uses artificial neural networks to process the very complex and highly non-linear process model of welding. And this is further used to generate code for the robot and deposit the material. Now, there are two major disadvantages of major gaps that were identified in the research that's currently taking place. One is that there is not enough study on the use of a tiltable bed. This tiltable bed can allow us to deposit material overhang features by tilting the material and depositing towards gravity normal to the extruded surface. This would help improve the surface called the surface roughness. There will be less amount of surface roughness, and the stair-stepping effect could be better controlled by this manner. So this is one of the areas. And the second thing is that there's a contradiction regarding whether the CMT process can be adequately used for manufacturing titanium alloy parts. So towards this end, through our research study, we have found that recently there has been a research group which used a rotating drum on which they rotated the deposited part to tilt the part and deposited it perpendicular to the direction of extrusion. And we decided to make it more comprehensive by using a hexapod. In this way, we can deposit in multiple directions with more complexity, and this can be aided by the use of a multi-direction slicing algorithm, which was again developed at the University of Wollongong recently. Next, so this would be the modified process plan for the end system, where we substitute the 3D slicing with the multi-direction slicing algorithm, and we have the hexapod code generation after the toolpath planning is done. So we can test this hypothesis by using an experimental research design. In this, we are combining the results from a computer simulation with that of experimental validation. So the experiment will take place in 4 stages, where we are combining the original system that was developed by the University of Wollongong with the CMT and the pulse spray GMOR process, as well as comparing it with the modified system that we are proposing using CMT and pulse spray GMOR process. And we have identified the equipment that we will be using for this. It involves the use of 2 robots. One is for weld deposition and the other is for milling operation at the end as a post-processing machining operation. The wire and the shielding gas compositions were selected based on previous research in this area, in which they were able to optimize the shielding gas composition to get better microstructure out of the titanium alloy additively manufactured part. We will be evaluating the performance of the system by using surface roughness, material utilization factor, and the time taken. The surface roughness will be measured by the use of a 3D laser scanner, and this data will be used to compare each of the 4 methods and make conclusions based on that. Some of the limitations of our design are the need for addition of a method to avoid the constriction of the built part with that of the robot while depositing in multiple directions, and also the use of multiple robots would add to the calibration errors, and also we do not study the residual stresses and microstructural properties. Thank you.